Okay, so it's almost 3 and we can start. Welcome to the uh, final extra live interactive session on the course Semiconductor Devices and Circuits, NPTEL NOC24 EE-143, uh, taught by the instructor Professor Sanjeev Sambandan from ISC Bangalore, and I'll be the TA for this session. And these are the email, I mean, the details you can use to reach out to me. And let's quickly go through the guidelines as usual. In case you have any query during the session, you can either raise your hand or you can just ask in the chat window. Please try to ensure that your microphones are muted, especially when you don't intend to speak. And uh, let's try to make this session an interactive one. And I would appreciate a cooperation from your side for the same. Uh, Please do keep pen and paper handy along with a calculator, as we will be solving some problems that would require some doing. Okay, and post this live session, the recording link of the session and the lecture notes will be shared by the NPTEL course team. Prerequisites include all the lectures that have been taught so far, though we would primarily focus on MOSCAP. I'll be showing some problems from MOSCAP section. So I'm assuming you all have already attempted all the assignments before tuning this session. So this is the first problem that we'll take up today. I hope this is visible. Let me still read it out. So an intrinsic silicon sample is doped with a position-dependent acceptor concentration, Ne of x, where Ne of x is your N0, 1 plus x by L. Uh, Wait, I'll draw this figure. So this is your figure, right? I'm trying to I'm trying to plot this, okay? Your Ne of x with respect to x. This is your N0 and this is your, I mean, some point corresponding to. So we have 2 points, x equal to 0, right? And x equal to L. And at x equal to 0, from this equation, we'll have N0, right? So the value that we'll have is N0. And then we'll have a suitable value at x equal to L. What will be that value? Can you quickly tell from this equation what should be the value of Ne of x at x equal to L? It's straightforward, right? Please either unmute or just type in the chat twice and not, yeah. So this would be, just consider this point using this. This is 2 times and not. Okay. So how should we proceed this one? For part A, we need to find an expression for electric field of x at equilibrium, right? For x equal to 0 to L, because L here is 5 micrometer. So we know that at equilibrium, your whole current density is equal to 0, right? We know that. This is what I'm trying to say. At equilibrium, I'll be using short notation. At equilibrium, the whole current density, Jp, right? Which is actually given by your Q mu P of X, electric field of X, and then you have minus Q dP, then your dP of X by dx, right? Now tell me one thing, uh, name this and this component. Which component is drift and which is the diffusion component? Right, your whole current density will be composed of first is drift. Yeah, this one is drift. And the second one is your diffusion component. Okay, so now the thing is this is at equilibrium, and at equilibrium this is equal to 0. So you can quickly, do the algebra and figure out that your E of X is given by your E of X is given by your dP by mu P, right? This would go here and mu P would go down. What else? I guess there would be your P of X, right? Wait, what else? Is this fine? Your electric field E of X would be given by this expression. Clear? Fine. So now our P of X, we can assume that our P of X is NE of X, right? And if I say so, what am I assuming? See, let me make the question clear again. I'm saying now I'll write P of X is NA of X, right? If I do so, what is the assumption that I have used in making this statement?
Almost all of the except dopants have ionized.
Yeah, so the assumption that I've used is 100% ionization, right? As you rightly pointed out. So, I'm doing it to simplify the calculation because then I can write E of X as your dP by mu P, which using Einstein's relation is dP by mu P is kT by Q, right? And kT by Q, yeah, let's write it as kT over Q. Now, what about 1 over P of X? Okay, your 1 over P of X should be, right? This is your P of X, which is, I just plugged this expression in the denominator. And then I need to differentiate it. What about d by dx of P of X? Let's do that together. The first term is a constant, right? So that won't be there in the derivative. What about the second term? Would you agree we'll be left with n0 by L?
Yes, sir, and 0 by L.
Yeah, it would be n0 by L. So I'll write n0 over L. But then this n0 and n0 would cancel out, right? So I'll be left with following. Your electric field of X would be, so this is kT by Q, right? Now be with me. So if I take LCM, this would be X plus L by L, and then that L and this L would cancel. So I'll be left with X plus L in denominator. Is that clear?
Yes,
Right?
sir.
So
Yes.
I'll write this 1
Into
by,
1 by x plus L.
yeah, 1 by X plus L. So, I mean, I, obtained the electric field expression at equilibrium, and this is valid from x equal to 0 to x equal to L. Now, if
Sir,
you
how did we get KT by Q?
okay, for KT by Q, I used Einstein's relation. You know this relation? dP by mu p is KT by Q.
Yes, sir.
That is what I
Okay.
used. I substituted this with this. That's it.
Then what was the use of assuming 100% ionization if we had to substitute the
The
given
reason
expression
is,
for?
if you don't assume 100% ionization, you cannot use, you need an expression for P of X. But the thing is, in the question, we were given an expression for any of X, right?
Okay, okay. Okay.
So
Yes.
that is the reason we assumed 100% ionization to make the process simple. For otherwise, we needed the fraction of the ionized, the fraction of the acceptor ions that were ionized. If we were given that, maybe we could have proceeded and computed P of X some way. But
Okay.
let's keep the thing simple. We assumed 100% ionization and we wrote P of X as NE of X and then proceeded from there on. Fine.
Fine, sir.
Okay. So now part two. Part two is simple and I would want you to try this out. Part B is that you need to compute E of X at X equal to 0 and 5 micrometer. 0 is simple, right? When X is 0, this is KT by Q 1 over L, right? And your L, what is L? L is 5 micrometer, right? L is your 5 micrometer. Is it? So,
Yes, sir.
okay, this was part A. For part B, electric field at X is equals to 0 is, can I get a number? Although this would be KT by QL, and that would correspond to, just do the math, this would be 52 volts per centimeter. Okay, I want you both to verify this because I only have two students that have joined live. Okay, then what about this electric field at X equal to L? This would be KT by Q. Do you agree? Yeah, half of the previous value. And since the previous value was 52, what is half of that? 26, right? So this would be your 26 volt per centimeter. Fine. Okay. Now, I mean, there is part C left, right? Which is actually the important one. This was actually build up. Part A and B were built up for the part C. Let's come to that part. Here is adding the page. Okay. Okay. Yeah, this one probably. Yeah. Now part C. So part C says that you need to sketch the qualitatively this band diagram, the correct band diagram, and then indicate what will be the direction of E of X for the given acceptor distribution. Okay, so how will you do that? Sorry. I mean, which expression would you use?
Majority carrier concentration expression.
Majority
Volt
carrier
carrier.
concentration expression. Okay, and then can you try that out?
Yes, sir.
Please try that out. What about you, Prasad Rao? How should we proceed on this one? Part C. How should we, qualitatively sketch the band diagram? In other words, I need an expression of that EI of X, right? Or EC of X or EV of X, anyone among them. Okay, see, if I were to approach this one, I would use this expression, right? You know that your electric field of X is your 1 over Q d EI by dx, right? Are you aware of this expression?
Yes, sir.
So what is EI? EI is how this intrinsic level varies with respect to X, right?
Yes, sir.
So I know the expression for E of X, right? So now using that, I can compute this EI of X. And once I know EI of X, the rest of the profiles, for example, the conduction band profile, the valence band profile, they will follow suit, right? Why? Because they follow intrinsic level, right? And why do they follow intrinsic level?
Both are equidistant from
EI.
intrinsic.
Yeah. So, I mean, that has to be the case, right? So, okay. So now that you know what is the expression for this uh, electric field of X, right? I mean, you know that your E of X, right? Now tell me what should be the expression for EI of X using this expression. I mean, I'm not looking for an exact answer, but what should be the nature of the function EI of X? How should it vary with X? Okay, let me help you out. Your, I mean, EI of X is a function which when differentiated with respect to X gives a function that has 1 over X nature, right? So what is, I mean, that function that when differentiated gives 1 over X dependence?
Log function.
Log function, right? So EI of X will have natural log dependence on X, right? I mean, there would be some function. I mean, one can figure that as well, but the thing is, we know the nature, right? And since we had to uh, see the question asked us to qualitatively sketch the diagram, right? So now we know that it would be, I mean, the behavior would be logarithmic, right? So I'll write following. I'll write that your e of x, this varies uh, inversely with x. Uh, Hence, EI and consequently EC and EV, right? They all will have logarithmic ln, I mean natural logarithmic, right? Dependence on x, right? So if I were to sketch that, wait, let me copy this one. If I were to sketch that, this is EF, this is your EC, This is your EI. This is your EV, right? This is how this would vary. Why have I drawn EF constant?
Equilibrium condition.
Hmm. So this is your ln of x dependence. Fine. Now the question is, there was a second part of the
So,
question
but
that you need.
why does the energy band bend only at x equals 0?
It's not bending. I mean, just ignore the way I have drawn it. It would, I mean, bend uniformly throughout in a logarithmic fashion. Just, I mean, I might have drawn it, but I do have, drawn it correctly. Why do you think it's only bending at x equal to 0?
Okay, due to the dopant concentration variation, as we move farther away from x equals 0, there's higher concentration of holes. Maybe due to that,
Okay, okay.
Fermi level is
I
closer
think
to E.
I was not able to get your question. Repeat your question again.
I was asking, could you just explain the bending
Hmm?
of the bands by showing the dopant concentration as well?
Okay, 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 okay. See, how, see, this was our NE of x, right? Your NE of x was N0. In fact, we have that, right? Why will I do it again? I have this plotted over here, right? So this is a linear function, right? And at x equal to 0, you have some particular value of N0. And as x increases, the value of Na increases. And when the value of Na increases, what happens to the nature of the semiconductor? Will it become more p-type or will it become
More
more
beta,
n-type?
more
Yeah,
beta.
and that is what is happening, right? EF is going closer and closer to EV as x is progressing, right? Look,
Yes,
here the distance is more, here the distance is less. So
yes. Okay,
this you can in fact say even qualitatively. The essence of the question was, how will it vary? Right? Will it vary linearly? Will it vary logarithmically? The other variant of the question would be, now you might be given some complex function of any of x, right? So the procedure will be same. This is how you will proceed and then compute how the bands will vary with x given dopant concentration. Is this clear?
yes, sir, clear.
Okay. So if that is the case, I guess we can move forward. Let's move on to the next one. So consider a PN junction in silicon. Okay, now this is a question from PN junction. Uh, just a second. I have taken questions randomly. I'll mention the name of the book later. If someone is interested in this subject, he can probably purchase it as PDF is not available. When is your exam scheduled, by the way?
November 2nd.
November 2nd. Fine. Am I audible? I guess I was disconnected for a while.
We can
Was
hear
I
you.
audible? Okay, fine.
Yes.
Okay, okay. Okay, so let's start this one. Uh, so you need to consider a PN junction in silicon. Na is given as 10 to the power 16 per centimeter cube. Nd is 10 to the power 15 per centimeter cube. You need to determine W, the depletion width, Xn0, where this Xn0 is the depletion width on the P side, and in Xn0 is depletion width on the N side, and then the magnitude of this Emax, right? What is the maximum electric field magnitude value? So these are the quantities that you need to compute, and you can assume that temperature is 300 Kelvin. First, you need to find W, right? How will you find W? We know that W is given by this expression, right? Right?
Yes, sir.
And sorry. And what is the unknown in this expression? I mean, Na
Built-in
we know,
potential.
yeah, built-in potential. And what is the expression for that? V naught would be your, I mean, your KT by Q, which is 26 millivolts at room temperature, and then you have ln of NA by Ni square, right?
Yes,
Why
sir.
can I use that? I mean, the reason I can use it is because this is PN junction, right? Had this been P plus N or PN plus junction, then I would not have been able to use this one, right? This I can use only when both the doping levels are comparable, right? PN. So now, what is the value of V naught then? Plug in the values and let me know. I'm assuming you have a calculator. You can take the value of Ni, intrinsic carrier concentration, as 1.5 into 10 to the power 10 per centimeter cube. KT by Q, you can take that as 26 millivolts. Na, it's given that Na is 10 to the power 16 per centimeter cube, Nd is 10 to the power 15 per centimeter cube. And when you plug in the values, the value of V naught that you would obtain is this, right? 0.637 volts. Now
So
you
what
will
is the value
plug
of Ni?
which Ni? Ni is
Yes, sir.
1.5 into 10 to the power 10.
Okay. Usually, would it be given in the question?
This is something that you should memorize because this is a fundamental. Even if you don't remember that 1.5 factor, remember that it's roughly 10 to the power 10 for silicon.
Okay.
This is something that you should memorize. Okay, now, yeah, and once you plug in the values, you'll get V0 as 0.637 volts. Now, why were we computing this built-in potential? Because we're interested in finding the depletion width, right? And now that we know V naught, can you tell me what is the value of this? What will you use the value for epsilon is?
11.8
11.8 and multiply by the
into epsilon naught.
into epsilon
8.854
naught. Yeah,
into
8.854 into, and
10 power minus
uh,
12.
would you keep it minus 12?
No, minus 14 for
Why?
farad per centimeter square.
Because I mean we are doing the calculations in terms of centimeter. The other way is you
Yes.
need to just, I mean, then you need to compute Na and Nd all in terms of per meter cube. Then I mean it would make sense, and the final answer would also be in meter. But the best way is use 8.85 into 10 to the power minus 14 farad per centimeter. That would make the calculation simple. Okay, so that was something that I wanted to point out, and then it's just plug and play, and then W is your 0.953 micrometer, right? Verify this. Also, what else were we supposed to compute? We were supposed to compute xp naught, right? What is xp naught and xn naught? Your xp naught is w nd whole divided by na plus nd, right? And you, if you put
Yes,
in
sir.
the
Right.
values, if you put in the values, what will you obtain for xp0? You'll obtain 0.087 micrometer, right? Verify that. Again, x and 0. Tell me what expression should I use for x and 0?
W into Na by Na plus N.
Yeah, yeah. So it would be W into Na by Na plus Nd, and that would come about as 0.866 micrometer. So xp naught is almost negligible in comparison to xn naught. And why do you think that is the case? Because,
Because Na is much higher than Nd.
yeah, it's around 10 times higher. So it's, I mean, the depletion widths, the ratio of the depletion widths would also be 10 times. It's charge balance, right? It is
Yes, sir.
xp naught into Na should be equal to xn naught into Nd. This is satisfied, right? This is charge balance. And then, okay, we are done with these as well. Now we are left with magnitude of the maximum electric field expression. What is the value of that? Sorry. Firstly, what expression would you use?
Twice the
This
built-in
mag
voltage by W depletion rate.
is the built-in potential by, yeah, I mean, you can use that as well. And the reason why you are saying so is because, just a second. Okay. So, I mean, you're saying so because the area of that has to be equal to built-in potential, right? So half of our base is the depletion width and altitude is Emax. Let's take magnitude. That is equal to built-in potential V naught. So that is the reason you are saying that your Emax is equal to 2 V naught by W, right? We're able to understand what I did there? No, probably not, right?
No, sir.
Wait, I'll explain. This, I guess I should remove it. You know this. So this is how E of x varies, right? Remember? Wait, I mean, I have not drawn this to the scale because on one side this would be having more slope and on the other side it would be having less slope, right? But I'm interested in first showing you how we arrive at this formula, right? So the point is this is E max magnitude, right? And when you integrate this, wait, I should draw this a little. Roughly somewhat like this.
The area under the electric field versus
Yeah, yeah,
distance
yeah.
graph is the potential.
Yep, yep. That is what I want to show, but I'll still show it properly so that others would also get it. This is your mines, xb0, and this is your xn0, right? And now when you integrate this, you get following, right? You get built-in potential, right? This is V naught. So your V naught, now does this formula make sense now? The area under this curve should be equal to this V naught. I hope this is clear, right?
Yes, sir.
Okay, so then this should also be clear, right? I mean, I just juggled the equation. Now, E max magnitude of the E max is 2 times V naught whole divided by W. So once you do the math, here this E max magnitude of it would be equal to, so this comes about as, verify this, okay? 13.4 kilovolt per centimeter. Okay, so we are done with this example as well. Let's move on to the next example. So consider a two-terminal MIS structure on a P-type substrate, doping concentration of 10 to the power 16 per centimeter cube. Assuming that there are no charges present in the oxide, you need to calculate the flat band voltage of the structure. Okay, now if it implies, I mean, there are two parts to this question. In the first part, it implies an aluminum gate whose metal work function is 4.1 electron volt, and in the part 2 we are using P plus polygate, right? And we assume that this Fermi level is coincident with the valence band for P plus polysilicon, right? uh, and the given data is that your q chi for silicon electron affinity, that is 4.05 electron volt. I mean, you are able to see the screen, right?
Yes, sir.
Okay, okay. I thought it was disconnected. And then the band gap for the silicon is 1.12 electron volt. This is the given information. Okay, so first I want to know how would you approach this, and then I'll probably show this. How should we approach this one? Anyone?
Flat band voltage would be the difference in the work functions of the metal and the substrate.
Good. So your VAB would be nice. So we have part A, right? And in part A, there is aluminum gate, right? It's given that Q phi m is 4.1 electron volt, right? And you just said that your VAB is phi m minus phi s, right? Assuming the oxide is free of charge, right? That is an assumption that we are using to use this equation, right? Because flat band voltage does have another component. If you consider the, I mean, if you're if you consider the oxide has some trapped charge, I mean, we'll ignore that part. Okay, so your VAB is phi m minus phi s. So the only unknown quantity that you have is phi s, which is, what is phi s?
Semiconductor's work function.
Semiconductor work function, right? Let's draw the band diagram. Okay, so it's a p-type substrate. Okay, so if it's p-type, where should the Fermi level lie?
Below the intrinsic, closer to the valence band.
Yeah, somewhere around here. Agreed? This would be your EF, this would be your EI, this would be your EC, this would be your EV. Right. Now, the question is, uh, okay, then there is vacuum level, right? And this magenta line or length is what is Q phi S. Do you agree?
Yes, sir.
Okay. So now what quantities are provided
Electron
to
affinity
us?
is also given.
Electron affinity is given, right? That is given. So we'll point out them using, I guess, yellow. This part is given. This is Q chi. What else is given?
The
What
band
else?
gap is given.
Band gap. And how can I make use of that?
EC minus CI could be obtained.
EC minus.
EI.
Good. So, I mean, Eg by what?
Eg by 2.
Right, Eg by 2 is given. What else? I mean, how? So the question boils down to this, right? I mean, I need to find this one. What is this?
That can be obtained from the doping concentration.
How?
Um,
I mean, you are on the right track. How? What is
the
the
whole
formula?
concentration expression could be used
Whole
equals Ni
concentration
times
expression.
exponential of
Okay,
um,
tell me that.
P equals Ni times exponential of
Exponential of
uh, Ei minus Ef by kT.
this expression.
Yes, and P could be taken to be Na itself.
Correct. So, I mean,
But I think
no, you are
Ni.
right. You are right. You are right. You are right. I mean, there is no catch in that. So, the thing that I'm trying to say is, okay, I mean, I won't change the approach. I'll let this be the approach. So, what he said, I'll continue onto that. I mean, you started from real scratch. I mean, I was expecting the formula for bulk potential because that would have simplified this, but still, it's better to start from scratch. It's fine. So P you said is can be used as Na, right? This as Ni, this as exponential Ei minus Ef by kT, right?
Yes, sir.
And then you can write this Ei minus Ef as uh, kT
kT ln
ln of Na by
Na
Ni,
by N.
right? Okay, this is what is called bulk potential, Q phi. Okay, in fact, bulk potential is phi f. Okay, I can write this, right? This is called bulk potential. You can even memorize this. What is phi f equal to in terms of energy difference? Difference between intrinsic and Fermi level. Okay, EI minus EF, an important quantity. So you can just memorize this formula as well. KT by Q ln of Na by Ni. Because that would save you some time, right? So yeah, once you know that, you can obtain phi f. So this is nothing but Q phi f, right?
Yes, sir.
And then now what will be Q phi s for us? I'll write here. Let's do one thing. Now we know how we obtained this, right? I can erase this off. Those who want to see can see the video. This is the quantity that we obtained. Those who know this can directly use it. Those who don't can do in the manner in which we did. So now, what is Q phi s now? Q phi s is, what should I write? I mean, this plus this, right? What is Q phi s?
Electron affinity plus band gap by 2 plus the surface potential. No, the bulk potential.
Yeah. So wait. Oh, for consistency of the units. Phi.
Sir,
And when
if
you
you are taking Q5F, Q5F will be in electron volts, right?
Q5 would be in electron volts, and so will be this affinity as well, right?
Yes. So in that case, Eg by 2 would suffice, right?
Yeah. Agreed. We don't need to eliminate that. I mean, I just confused it. Here I wrote it as Eg by 2. Okay, now what is the value of Q5s that you would obtain? This is 4.96 electron volt. So what is VFB then? Phi m minus phi s. 4.1 minus 4.96. Are you getting it?
0.86 minus 0.86.
Minus 0.86. So volts, right? I mean, I removed Q, right, from both. So it won't be in electron volts, it would be in volts because it's phi m, not Q phi m. And this is phi s, not Q phi s. That's why the E from electron volts can be removed. So this would be in volts. So that finishes part A. What about part B now? What about part B? What thing will remain same for part B?
Electron affinity.
Even more than that. This whole phi s would remain same, right? The only thing that we are changing is gate, right? Now we are using a P plus poly gate. In the question, it is not mentioned that you are making any change to the semiconductor. So the semiconductor is same. I mean, the only way to change the work function is to alter the doping. If you don't play with the doping, the work function will remain same, right?
Yes, sir. Yes.
So your phi s is same. What about phi m? So the now question now boils down to obtaining phi m for part B, which is P plus polygate. But it's given that for P plus polygate, your Fermi level is coincident with the valence band. Okay,
Okay.
so it's affinity plus the band gap. Did you got it? Metal work function.
Yes,
So
sir.
imagine this is a metal, which is a polysilicon metal, right? And in this P plus polysilicon, your this Fermi level is coincident with the valence band. So till EC it was chi, Q chi, and from EC to EV it's EG. Did you got it?
Yes, sir. And
So so for this one I'll write what is my Q phi m? My Q phi m would be equal to Q chi plus
EG.
EG. And what is Q chi? 4.05 electron volt. What is EG? 1.12 electron volt. Sum them up. What is the value? 4.17 electron volt, right? So this is 4.17 electron volt. Now, so what is VFB then? It's phi m minus phi s. Your phi s was 4.96. Your phi m is 4.17. 4.17 minus 4.96. What is the value?
minus 0.79.
Mine's zero point 0.7. Is it? Oh, I guess I did a mistake. This would be 5.17, right? We did not point this out. This would be 5.17, right? Because QChi is 4.05, and if you add 1.12 to it, it would be 5.17,
Yes, sir.
right? And when you subtract 4.96 from 5.17, now just tell me the answer, what the answer is.
0.21
0.21. So this is 0.21 volts.
volts.
Fine. Yeah, volts. That is what I wrote. So that is how you do this one. So now what I want you to do is, this was a 1 hour session, right? I mean, although I had planned to show 2 to 3 problems more, try them out. And if you are uh, not able to solve it, let me know. I'll send the solution tonight to those who mail me. Okay. These will be the slides that I'll be uploading, and those who are interested can try these problems and let me know if they are not able to solve it, and I'll send them the solutions. And also, I should note this one. Let me add an acknowledgement. I mean, for this one, oh, I guess I made a mistake. Now it's fine. So the example problems that I took for today's lecture were from this book, Semiconductor Devices and Circuits by Alok K. Datta. Those who are interested in this subject, semiconductor device and circuits, I mean, if you aim to, I mean, if you are a UG student and you aim to venture into PG and be in this field, you can read this book. This is a good book, and the only catch is there is no PDF available, so you'll need to purchase this one, right? And this is from Oxford Publications. That's it. Okay.
So, if you're interested in pursuing PG in this field,
Hmm.
which PG should we do? I mean, could
Which
you name the
PG
program?
programs? The two PG programs that you can pursue is either you can pursue masters, MTech or MS. I mean, if you are inclined towards research, you can, and you are not sure about a PhD, you can pursue MSc. Okay. And if you, I mean, if you want to uh, do PG and then improve your skills and get into industry, you can pursue MTech. And if you are sure about research, you can even do a direct PhD. Those
So
programs
I
are
was
also on.
doubtful about the name of the particular MTech program, like
Name of the
nanotechnology.
Okay, this would be okay. I mean, I'll tell you about my college. This specialization is named as microelectronics and VLSI. Okay, and this would, I mean, in most of the institutes, this would come under VLSI or microelectronics, either of the two. In our college, it's microelectronics and VLSI.
Okay, sir.
Are
Thank
you
you.
interested towards uh, devices more or circuits?
Um, Devices.
Devices, right? Uh,
Yes.
Try to see if the college have microelectronics as a specialization in EE department or ECE department. That is a domain that you should get into if you're interested in this semiconductor devices field. And yeah, I mean, you can either apply for a direct PhD or you can apply for an MSc if you just want to see how things would go up. One
Okay,
can
sir.
usually convert MSc to PhD as well. I mean, most of the colleges do offer that option as well.
Okay.
Yeah.
So then I had
Hmm.
some doubts in assignment 12, last
Uh,
assignment.
Assignment 12. Okay.
Yes, sir. Regarding the answers, I was doubtful whether those were correct.
Uh, that's not
The answers
regarding the
have been
live
published.
session, right? The assignment that the instructor uploaded, right? You're talking about that assignment, right?
Yes, that is it.
Okay. So, uh, did they not send you the answer key?
No, the detailed solution is not yet uploaded.
Answer key. I can understand the
Answer
detailed
key is
solution.
given,
Okay.
but
So,
I have doubt whether it's correct
okay, you have doubt whether it's
for
correct or
three
not.
questions. Yeah, I brought up the issue on forum but did not get any reply. I mailed
Did you
sir also.
you mailed sir? Did you mail the NPTEL team as well?
No, I didn't know their email ID. I mentioned that in the forum, but
Okay. Mail
I
me.
mentioned that
Mail me
last week
those
itself. But
questions.
okay, sir.
Mail me that query as well.
Okay. One
If
one
I'm
of
not
those questions was also discussed in one of the live sessions
okay.
last week. Live session, sir.
Okay, live session last week. That I can
Yes,
probably see. Just a second. So that was week 12, right?
week 12. Yes.
This is week 12. So which question was it?
One based on TFT.
Based on TFT. This one?
Yes, sir. This one.
Okay.
Sir, here I feel that deep trap states also contribute in conduction mechanism because that was mentioned in one of sir's slides.
If sir has mentioned it, then take that as the final word. I
Okay,
mean,
sir.
whatever I think doesn't matter, right? If sir has said that they contribute to the conduction mechanism in amorphous semiconductor, take that as the final word.
Okay, sir. Sir, similarly, one more question.
Then even this would change, right?
Yeah,
Then question 4 would also
this was
change.
also there in the assignment.
Okay. Okay, this was in assignment as well.
Yes.
And what was the answer key?
Answer key is as provided by you, sir.
That is
Extended
what
and
I'm
mailed.
saying. I mean, as far as I know, deep state shouldn't have contributed to the conduction mechanism in
But
amorphous
in sir's slide, it's mentioned that there is hopping conduction
mechanism.
in deep state.
Okay, yes, hopping mechanism is there. Variable range hopping. See, if sir has categorically mentioned in the slides, did you mail the instructor regarding that your
Yes,
slides
I had
contain
mailed.
this?
Yes, but
Okay,
didn't get any reply so far.
I mean that is up to instructor. I mean, uh, all I can say is I can go through it again, but uh, let's hope the instructor will reply you in time. And
Okay,
in the exam as well, whatever sir has taught, stick to that. If
okay. So then
if
there's
if
yet
whatever
another.
if whatever
Okay,
I have said in the live sessions that contradicts with what sir has taught in the slides, I mean, forget what I taught and go with whatever sir has taught you.
okay, sir.
Yeah.
So there was
Yeah.
one yet another question
Which question?
discussed in the live. One based on threshold voltage, where we compare threshold voltage of um,
This one?
crystalline and amorphous
Crystalline
materials.
and amorphous. Okay.
Yes, sir, this one.
Hmm.
Here,
Yeah,
the
please.
option A is said to be correct, but I think that condition holds for crystalline semiconductors. Because for
Sorry.
amorphous, it should be option B. In amorphous, I think we do not have inversion and strong inversion.
Yes, I would. Uh, I'll look into this. What about the sir? I mean, I did not get chance to see those slides. Has he mentioned this somewhere in the slides?
Yes, sir. He has mentioned
If he has
that.
mentioned it, yes, then you're right. It's part B. Uh, I mean, let's
Okay.
make this a correction. Or just do one thing when I'll upload the video, add the comment on whatever
Okay.
questions we discussed and on whatever we finalized, so that even if I forget, there'll be a comment for others to see. Fine.
Okay. Fine.
Any other question? Thanks for
No, sir.
taking these questions up and bringing this to attention of others as well. So these were the ones, right?
Yes, sir. These three.
Okay, okay. Thank you, thank you. Okay, if there are no further questions, then we'll probably end this session, which was our last uh, interaction on this series. Any feedback?
All the sessions were pretty good, sir. We enjoyed it.
Thank you. Thank you. Yeah, if you have any further questions or if you have any further queries, feel free to reach out to me via mail. Okay.
Sure, sir.
Even if you need any help regarding any guidance to get into PG programs, feel free to mail me. I'll be
Okay, sir.
there to help you out. Okay. Thank you. I'll be ending the
Thank you,
meeting.
sir.
Bye. Bye.
Bye, sir.